Click the bell icon to get latest videos from Ekeeda.
Hello friends, welcome to the subject of Machine Design 1. We are right now solving a numerical on design of turnbuckle. In last lecture, we had seen the design load, then material selection and the design of tie rod. In today's lecture, we are going to start with the design of coupler nut and then we'll proceed to the design of coupler. So let us begin. So in part number 2, we are going to start with the design of coupler nut. Now, when we say design of coupler nut, we are associated with two important values. They are D and the length of nut. So let us begin with it. Now here also we have to consider two different modes of failure. Again, tensile failure and shear failure. So when we consider tensile failure, we know that the axial load P will be given by the projected area. Now this time the projected area of the nut will be equal to pi by 4 its outer diameter square minus pi by 4 its inner diameter. Now inner diameter we are considering the diameter, the outer diameter of the tie rod. So it comes out to be d square into its failure criteria, which is tensile failure. So it comes out to be sigma t or sigma allowable. Here if you take it out common, it becomes d square minus small d square into sigma t. Let's substitute the values which we have. The value we had found out, the design load was 32 kilonewton. So 32 into 10 raised to 3 is equal to pi by 4 into the unknown factor minus the known factor, which we have found out is 28 millimeter square, into the allowable value which we have is 84. So as we solve this value, we'll get answer. So as we solve that equation, we'll get value of D equals somewhere around 35.62 millimeter. Again, going for the round of value, we'll take that D is equal to 36 millimeter. So that is what the finding of our diameter of this coupler nut. Now we have to go for the length of coupler nut. So there we consider the shear failure. Now when we know that shear failure comes into picture, we again consider the axial load, and axial load in terms give us the shear failure. The shear failure is basically the projected area for the shear, which is the circumference into the length into the shear allowable value. Since this is an unknown for us, we have to use the value and find out the safe value of length. Otherwise, in other terms, if we have some empirical relationship, we will find out length. We'll substitute in this formula and we'll see whether the value of shear stress that comes out to be is safe or not. And therefore, substituting the value 32 into 10 raised to 3 equals pi into. Now DC is nothing but the core diameter, because that is what we are going to consider for shear failure, because that is the most delicate part of this particular assembly, nut and bolt assembly. If you can understand it properly, the coupler nut and the tie rod, when they assemble, that's nothing but the nut and bolt assembly. So into DC value which we have found out is 24 mm into the length which is unknown into the allowable value of shear, which came out to be 42 Newton per millimeter square. The value of length which we get after solving this expression is 10.105 millimeter. Let us round it off to the next level and let us say length should be at least 11 millimeter for sustaining the given strength. So why length I am increasing, that also an aspect. Some people may say let us take smaller than that, let us take just 10. See, if you see properly, the length is inversely proportional to the allowable value. So as length goes on increasing, the value which is induced, it's not allowable, it's the induced value. So as the length goes on increasing, the induced value of tau goes on decreasing, and hence the material becomes safe. If I go for reducing the length, the induced value of tau will be greater than the allowable value, and that's why I have to take the next level or the next round of version of length. So length of your particular rod should be particular nut should be 11 mm on either sides. So let's go for the last part of this, that is nothing but design of. Here we are going to look at the different dimensions of coupler. Very important dimension is D1, D2 and the length of coupler. Now here also there is some empirical relation that we are going to use again from the computer-aided machine drawing book, and that says that the inner diameter of coupler is almost equal to the outer diameter of rod plus 6 millimeter. You can say standard practice. See guys, when we say standard practice, it's not something that we lie about. It is something that is experimentally proven already and that we are going to use directly. Now since that experimental proof or the proof of that particular empirical relation is not the scope of our journey, we are not considering that, we are not looking at it. So we are directly using this particular standard practice, which is completely safe, so you need not worry about where this relation came from. If you want to refer to the actual origin of this particular empirical relation, you can actually refer to the machine drawing books. There you will get this idea. So let's move ahead. So D1 comes out to be the core diameter small d, which we found out was 28 millimeter plus 6. So therefore D1 should be, according to the empirical relation, 34 millimeter. Now we have to consider the failure. Now it's nothing but the tensile failure. So considering tensile failure, we'll get this relation. Tensile failure takes place because of the axial loading, which is equal to the difference between the area. So it is the outermost area, so d2 square, minus innermost area, d1 square of the coupler into its tensile strength, or you can say the allowable strength. So as we move with it, we have these values with us. We have to find out d2 value. So as we go ahead, we get, therefore is 32 into 10 raised to 3 is equal to pi by 4, we can take this common, d2 square minus d1, which we have found out is 34 millimeter square, into its tensile strength, which is 84 millimeter. So as we solve this relation, we get value of d2 somewhere equal to 40.51 millimeter. Let's round it up to the next value, because the value of d2 is again inversely proportional with the shear strength, and that's why we can take the higher value. So d2 comes out to be 42 millimeter. That is what the finding we have. The last finding that we are going to look at is the length of coupler. So whenever length comes into picture, we will go for the consideration of the projected area along the length, which is nothing but the shear failure. So we are going to consider shear failure. Now we are going to use the empirical relation directly. That gives us the length of coupler should be somewhat equal to, or should be approximately equal to, the outer diameter of your tie rod. And therefore with that relation we'll go ahead, it comes out to be 6 into the tie rod diameter, that was 28 in our case. So the length of coupler is equal to 168 millimeter, and this is how we'll get the answer for the length of coupler. Now that is the finding about all these problems. They we actually end with the problem, but it's better you always summarize your findings. So we had selected the material C60 with its material properties. That was the first finding. Second finding we had was the core diameter, which was 24 millimeter. Then we found out the diameter of the tie rod, outer diameter, which came out to be 28 millimeter. So both of them belong to tie rod. Then we went for diameter D of your nut, which was equal to 36 millimeter, and the length of the threaded portion of nut, which came out to be 11 millimeter. So both of these parameters belong to coupler nut. Thereafter we went for D1, which came out to be 34 millimeter. It's the inner diameter, of course, and make sure that D1 is smaller than D always. And then D2 came out to be 42 millimeter. And the last parameter we found out was the length of coupler, which came out to be somewhere around 168 millimeter. So all these three parameters belong to coupler. So that is how we found out the material. We found out the safe allowable values of tensile and shear stresses, and based on these allowable values only we have found out these answers. Of course, no doubt, it started with the safe values. The dimensions which we have found out are safe. So that was the design numerical on tie rod and turnbuckle. In our next lecture, we'll be dealing with the design aspects of power screws. We'll go through the important formulae and then we will solve a numerical on power screw. Thank you so much for watching this video. If you like this video, please subscribe to Ekeeda.